Hello, I am Victor. Today we'll uncover the mysteries of solar storms, what they are, their impacts on Earth, and the looming threat of an incoming solar storm. Solar storms are powerful bursts of energy and charged particles that originate from the Sun and can have significant effects on Earth's magnetosphere, ionosphere, and the technologies we rely on every day. These storms are caused by solar flares and coronal mass ejections, CMEs, which are associated with the Sun's magnetic activity. When these events are directed towards Earth, they can lead to geomagnetic storms and have the potential to disrupt communication systems, power grids, satellites, and even pose risks to human health. Solar storms, also known as space weather events, are indeed fascinating and potentially dangerous phenomena. They are caused by the Sun's activity, which includes the release of vast amounts of energy and charged particles into space. There are three primary types of solar storms: solar flares, coronal mass ejections, CMEs, and solar energetic particles, SEPs. Solar storms are the result of complex processes and interactions within the Sun's magnetic field and its outer layers. The Sun's magnetic field is generated by the movement of plasma in its interior, specifically the convective motion of charged particles in the solar core. This movement creates a dynamo effect, which leads to the generation of magnetic fields. The magnetic fields on the Sun's surface are not uniform, and they can become twisted and tangled due to the Sun's differential rotation. The equator rotates faster than the poles. This twisting of magnetic field lines can lead to the formation of sunspots, which are cooler, darker regions on the Sun's surface where the magnetic field is highly concentrated. Solar storms, including solar flares and coronal mass ejections, CMEs, are triggered by the release of magnetic energy stored in these sunspot regions. Solar flares. Solar flares are intense bursts of radiation from the Sun, spanning the entire electromagnetic spectrum. They result from the rapid release of magnetic energy in the Sun's atmosphere, which can disrupt radio communications, satellite operations, and change the trajectories of low Earth orbit satellites. The radiation from solar flares travels at the speed of light. When magnetic energy builds up in sunspot regions, unstable magnetic field lines can suddenly reconnect, releasing vast amounts of energy and causing solar flares. The energy released in a solar flare is immense, equivalent to millions of nuclear bombs detonating at once. Solar energetic particles, SEPs, these high-energy particles, primarily consisting of protons and electrons, are accelerated by solar flares or shock waves associated with CMEs. SEPs can travel at exceptionally high speeds, with some reaching up to 80% the speed of light, or approximately 240,000 km per second, though the majority have lower velocities, typically ranging from a few tens to hundreds of kilometers per second. When SEPs reach Earth, they can pose a radiation hazard to astronauts, satellites, and electronic systems on board spacecraft. Coronal mass ejections, CMEs, are large eruptions of solar plasma and magnetic fields from the Sun's outer atmosphere. They release massive amounts of charged particles into space and can travel at varying speeds, typically between 200 and over 2,000 km per second. CMEs can occur due to the release of magnetic energy in sunspot regions, when twisted and stressed magnetic field lines expand outward from the Sun's surface, propelling solar plasma and magnetic fields into space. If a CME is directed towards Earth, it can interact with our planet's magnetic field, potentially causing geomagnetic storms that can disrupt power grids, satellite systems, and communication networks, as well as generate auroras. The Sun's magnetic activity plays a crucial role in the occurrence and intensity of solar storms. The Sun's magnetic field is generated by the movement of plasma within its core, leading to the creation of sunspots and other magnetic phenomena. As the Sun undergoes an 11-year solar cycle, its magnetic activity fluctuates, leading to periods of increased or decreased solar storm activity. During solar maximum, the Sun's magnetic field is more active, resulting in a higher frequency of solar flares and CMEs. Conversely, during solar minimum, solar storm activity is generally reduced. Understanding the Sun's magnetic activity and its role in solar storm formation is essential in predicting and preparing for potential space weather events. Auroras are natural phenomena that occur when charged particles from the Sun interact with Earth's magnetic field, causing a colorful display of light in the sky. Strong solar storms can release a large amount of charged particles towards Earth, which can result in auroras being visible at lower latitudes and even in regions where they are not normally seen. If we were to see auroras all over the world, it would indicate that a significant solar storm has impacted Earth, resulting in an increased frequency and intensity of auroras. Solar storms can be detected and monitored in real time using various instruments and techniques. For example, ground-based observatories and satellites can measure the sun's magnetic fields and activity levels, as well as detect changes in the solar wind and other indicators of solar activity. These measurements can be analyzed and used to forecast potential solar storms with varying levels of accuracy, depending on the complexity of the storm and the sophistication of the forecasting tools. While some solar storms can be detected and forecasted days in advance, others may only be detected hours or even minutes before they impact Earth. Rapid detection and response to solar storms is crucial for minimizing their potential impacts on critical infrastructure and systems. The KP index is a scale used to measure the intensity of geomagnetic storms. The scale goes from 0 to 9, with 0 indicating low activity and 9 representing extreme activity. The KP index is based on measurements of Earth's magnetic field at different locations. The National Oceanic and Atmospheric Administration, NOAA, uses the KP index to classify geomagnetic storms into different levels: G1, minor; G2, moderate; G3, strong; G4, severe; and G5, extreme. The higher the storm level, the greater the potential impact on Earth's systems and infrastructure. Solar flares are categorized based on their peak X-ray emission in the 1 to 8 angstrom wavelength range, as detected by GOES satellites.
There are 3 classes of solar flares: C, M, and X. Each class has a number from 1 to 9 to show its strength, except for X-class, which can go beyond 9.
C-class flares are the weakest, while X-class flares are the strongest and can cause significant impacts on Earth's systems and infrastructure. Solar flare classifications provide information about potential impacts on radio communications, satellite systems, and other technology that may be affected by high-energy radiation. Classification systems such as the KP index for geomagnetic storms and the X-ray solar flare classification system help assess solar storm impacts and improve forecasting and preparedness measures. Monitoring these classifications allows stakeholders to make informed decisions about protecting critical infrastructure and ensuring safety during solar storm events. Solar storms can have various impacts on Earth, including effects on the ionosphere and magnetosphere, disruptions in communication systems, reduced GPS accuracy, vulnerabilities in power grids, and satellite damage. These storms can disturb Earth's ionosphere, leading to radio blackouts and signal degradation, while also affecting GPS signal propagation. Geomagnetic storms can induce electrical currents that can flow into power grids, causing voltage fluctuations and potential blackouts. Additionally, satellites are vulnerable to high-energy particles and radiation from solar storms, which can result in malfunctions, reduced lifespans, or complete failures. Solar storms can also impact human health, aviation, space travel, and critical infrastructure. They pose risks to astronauts and air travelers at high altitudes due to increased radiation exposure, which can lead to radiation sickness and other health issues. Solar storms present challenges for aviation and space travel by affecting aircraft electronics and communication systems. Moreover, they threaten critical infrastructure, such as power grids, communication networks, and transportation systems, making it essential for governments and industries to understand their potential impacts and take appropriate preparedness measures to ensure the continued operation of essential services during space weather events. A minor geomagnetic storm, G1, is expected for the next 24 to 48 hours, which could cause small changes in the power grid and minor effects on satellites. However, people living close to the poles, 60 degrees geomagnetic latitude and above, might witness the northern lights, aurora, in certain parts of the US like northern Michigan and Maine. But don't worry, the G1 grade is the lowest level and there is no need for concern. One of the most intense solar storms is the Carrington event, named after British astronomer Richard Carrington, who observed the associated solar flare, was a powerful solar storm that occurred in September 1859. It is considered one of the most intense solar storms ever recorded. The event was caused by a massive CME that was directed towards Earth, leading to a severe geomagnetic storm. The Carrington event had several notable effects on Earth. The geomagnetic storm led to spectacular auroras visible over much of the planet. The auroras were seen as far south as the Caribbean, an unusual occurrence since auroras typically appear at higher latitudes. In some areas, the auroras were so bright that people could read newspapers by their light at night. The Carrington event's most significant impact was on the telegraph systems of the time. Geomagnetically induced currents generated by the storm led to widespread disruptions, malfunctions, electric shocks, sparks, and even fires in telegraph networks. Some telegraph systems continued to function when disconnected from their power sources, powered by the induced currents from the storm. Fortunately, there were no light bulbs at that time, as the light bulb was invented 1 year after the event. which potentially prevented further complications. If a solar storm of the same magnitude as the Carrington event were to occur today, the consequences could be far more severe due to our increased reliance on technology and electricity. Modern power grids, satellite systems, communication networks, and other critical infrastructure could be at risk during a powerful solar storm, potentially leading to widespread blackouts, disruptions in communication, and damage to satellites. The economic impact of such an event could be significant, and recovery efforts could take months or even years. In 1994, a solar flare damaged the GOES 5 weather satellite, leading to a loss of communication. In 1989, a geomagnetic storm caused by a CME led to the Quebec blackout, with millions of people losing power for hours due to the collapse of the Hydro-Quebec power grid. The 2003 Halloween storms resulted in temporary communication loss with several satellites and affected GPS accuracy, impacting industries like aviation, transportation, and emergency services. These examples highlight the importance of understanding and preparing for solar storms. Solar storms are fascinating yet potentially dangerous phenomena that can impact Earth's systems and technologies in significant ways. By understanding the nature of solar storms, their potential impacts, and the importance of preparedness and international cooperation, we can better safeguard our planet and its inhabitants from the potential hazards of space weather events. Thank you for watching. I will see you in the next video.